So welcome everyone. Today, this talk I'm going to try to introduce and motivate what Watanabe calls in his great book, Main Formula 1, which is this formula written in written in brown here. So this is going to be a kind of a softer talk to introduce and with more illustration and motivation than actual technical details, and it might be I might throw some questions to the audience about exposition and how these things are presented, because there are some points in this story that I don't really have a good idea of why it is introduced this way. The the ultimate result is undoubtedly useful, but the path towards it is perhaps not as clear to me as I would like it to be. All right. So let's start. So we'll go through some illustration of the effects of what random sampling of the training data do to the log loss function and to the posterior, and therefore to the posterior. We will motivate the need for main formula 1 because of our intention to study the random sampling, and then we'll outline a proof for main formula 1. So just some brief recap. So in statistical learning theory, we are studying systems, like a machine or our brain that perceives in some sense by perceived data generating process. So these are the data generating processes which we denote Q. These are data generating process with stochasticity in there, so it is a distribution. So these are some examples of images with labels and the handwritten digits with labels and so on. The perception would be a bunch of data set generated by a bunch of data points generated by the data generating process. And let's go to the next part. Oh, I wasn't attached a speaker. Let me do that. Okay, so we have the truth generating data set, and our goal is to have a statistical learning process that produce a guess, an estimate that approximates the truth, right? So our way of doing this is again via a parameterized model. So this process here, this error here is kind of factored into two steps, which is we have a model with a prior. So each point in this parameter space is a model, and this defines an important quantity called the log loss function. Let's recall its form again. Oops. Negative. And some of the ways that we can get from the log loss function to p hat, our goal is, say, via minimization or taking averages. So that's the minimization is using the maximum likelihood estimate, and taking averages is the Bayesian predictive model. That's saying that let p hat x equal to the Bayesian average, the Bayesian average over Bayesian average of a likelihood function over the posterior. Okay. Right. So the role of statistical learning here is the role of theory from this picture is to clarify the behavior of this function, because as we see here, any inference method, be it minimizing it or taking the Bayesian posterior, involves it. Just to remind ourselves, the posterior here is written in our preferred form is -n. So the likelihood that the log loss enters in that way. Okay. So we first, instead of studying ln, we will study a kind of a centered version or a normalized version of it, which is by subtracting its minimum, where W naught is in the set of minima of ln of the log loss. Or in a realizable case, this is just this is equal to the entropy of the truth. Okay. All right. So immediately to study this log loss function, or in our case to study Kn, the normalized version, we note that just law of large number implies that Kn will converge to, if the mean exists, converge to its mean, right? Which is the familiar K function here. So there is already a kind of expositional question here, which is what happens in the unrealizable case. So this quantity here, this term here will just become P of x of W naught, and that Q of x remains. And the exposition go via that. Okay, right. Let's go to the next board. The other thing that we can immediately see is using the central limit theorem. Central limit theorem says that if you scale Kn appropriately and centralize it, Kn, centralize it with its mean, and scale it with root, and this converge in distribution to a normal distribution. Let me say that way first and see what the variance of this distribution is. Well, if you go through the central limit theorem calculation, the variance is just the variance of the terms making out Kn, which is this expression here. So that's the term making up Kn, and subtract it. So that's that's the expression for the variance. So, and it's a function of W. So what happened? Let's see what happened when we substitute in W naught or anything that makes Px of W naught Q of X. So the set of true parameters. Well, we get this thing becomes 0 in that case, and that thing becomes 0 in that case, and well, the whole so that's 0, and well, that means that it's actually undefined as a normal distribution at the in the set of true parameters. So this is really just this convergence is a pointwise convergence. So this is for each. This only holds for each W in the set away from the true parameters. We can actually do better using stochastic process theory. I think there's a theorem called Glivenko-Cantelli theorem that makes this convergence uniform in W, but still away from W naught, away from the set of true parameters. Okay, let's, before we go too far with building this theory, let's go and look at some illustrations of how this works in some specific example. Let's go to some of the plots. Let's go to the plots with a bunch of the order is not coming. Okay, cool. Right. I think, yep, I think everybody's here. All right. So so this is an illustration of a particular kind of model. In this case, it is just data generated from a normal distribution. So Q of X. Oops, use a black. So Q of X in this case is just well, is just normal with a particular mean, with the true mean and true sigma, and the class of model. Oops. The set of model is also. I'm committing the same kind of terminology sin as people usually did with like using model in multiple different ways. But anyway, what I wrote is what I meant. That okay. So and the top part here, the top series of images are the case where n is equal to 20. So the training sample size is 20, and each different images, each four of these images are different draw of the set of 20 training samples. And what you see plotted here is the contour of the likelihood function. So and if you mentally flip the meaning of the darker and lighter part, this is somewhat like the contour of the log loss function, but this is the likelihood, right? And the diamond here you see is the true parameter. It's well, it's W naught, which is equal to mu naught and sigma naught in our case. Okay, so some observations, right? So throughout the four different plots, it is clear that the likelihood function fluctuates. It changes with training sample. This is what we meant by the likelihood function being a random variable. Well, it is the measurable function of the training sample, hence a random variable. And so you can see that if I can use crosses to highlight the NLE estimate if in each of these cases, and you can see that it is not exactly at the truth. But we do have, if we look at the next plot, Oh, sorry. Sorry. The top plot is n equal to 50. That's the one with higher, and you can see that because it has tighter distribution around the true parameter, right? And that's kind of the point that I want to illustrate, which is as n gets larger and larger, the fluctuation around the truth, in this case, in this particular case, which is a regular model, it concentrates around the true parameter. So this picture illustrated the most likely parameter is not the true parameter, but as n goes to infinity, the true parameter becomes the most likely parameter. And this property is called asymptotic consistency. And furthermore, as n becomes larger and larger, the distribution becomes more and more like Gaussian. So, and this property is called asymptotic normality. And furthermore, because of regularity, we can prove that the fluctuation around, so the distribution of parameters around the likelihood, so around around the true parameter, is as tight as possible. So this width is as tight as possible among all other possible consistent estimators, a consistent prediction of the true parameter, and that's a property called asymptotic efficiency. And these properties are very much related to the asymptotic consistency, normality, and efficiency. These are very much related to the fact that in regular model we have local quadratic approximation. So K of W is locally approximated by a quadratic form. In fact, it's W transpose once you centralize around the true parameters. Okay, so this is regular model, and now let's go to a singular model. Next example, which is, let's walk to the left. Okay, so this model, I will write it somewhere on the picture. This model is a regression model of a 10-hedge regression, right? The dependent variable is y, and the independent variable is x, and a and b are the parameters, and we're assuming that the residue is this is a normal. So the noise of measurements of this process, which follow the law of y equal to a 10h bx, the measurement noise is distributed as a normal distribution, normal with variance 1. All right. So some observation, right? This is if we look at the fact that there is a symmetry across this line. There's a mirror symmetry across that line. That's because this equation here, well, the 10h is an odd function, right? So therefore it is symmetric under the transformation AB goes to -a, -b. Right? And this immediately says that this is not a regular model anymore. It is not identifiable, right? So which means that these distribution is definitely not Gaussian, even asymptotically, because it has two mode, right? it has two peaks even asymptotically. So it is definitely not Gaussian, but sorry, again, the square is the true parameter, but locally around the true parameter, asymptotically, you can, if you just focus on that part, a Gaussian approximation is still good, right? Because locally, the Fisher information matrix there, or the KW function there is not, the Hessian is not degenerate, and therefore quadratic approximation near the true parameter in this case is still good. So I should probably say that going from, let's divide this picture up into two parts. Going from the left to picture to the right to picture, the thing that has changed is that the training sample size goes from 500 to 5,000. So you will see that the right hand distributions are tighter. And going from top to bottom, the true parameter move closer and closer to the axes. And on the bottommost plot, the true parameter is on the axis, while it's on the set AB equal to 0. And what's special about the axes is that in this model, if you calculate the Fisher information matrix, AB equals 0 is precisely the set where the determinant of the Fisher information matrix becomes 0, or when is where the Fisher information matrix fails to be positive definite. Those two are equivalent statements. Here's a expositional question for people, which is that we don't really have a name for this set. We have a name W0 for the set of true parameters, and that coincides with this set when the model is actually singular. So be careful in this picture that everything above the bottom row, everything above the bottom row is actually not not regular model. So it's actually have a positive definite Fisher information matrix near W0. Except that they are not identifiable, hence they are not regular. But the bottom row is the truly singular model. And what distinguishes those two cases is that in the bottom row, not only do we have non-identifiability, well, the non-identifiability becomes the whole set, right? The whole AB equal to 0 becomes, so when AB equal to 0, the whole 10H term disappear. A or B equals 0, the whole 10H term disappear, and this whole axis represent the same distribution. That's non-identifiability. But even worse is that near the true parameter, near any of these parameters, there are no local quadratic approximation. So even locally, quadratic approximation or Gaussian approximation to the posterior fails.
Maybe there's one thing I think is helpful to remind people, which is that I depends only on P, on the model, and not on the truth, as opposed to K, which depends on the truth. So maybe you said that already. But
no, I haven't. But that's exactly the point. Yeah.
Yeah. So by focusing on where the Fisher information matrix is degenerate, what Edmund is doing is saying, so two facts. So remember that near a true parameter, the KL divergence locally looks to second order like the Fisher information matrix. So what Edmund is doing by showing you where the Fisher information matrix is degenerate is saying if you place the true parameter there, then K won't have locally a quadratic approximation. exactly because to second order it will look like this matrix, and you've put a point where that matrix is degenerate. So there's a, which is, I guess sometimes we're often starting with K and thinking about K, where you're sort of starting with the model and the Fisher information matrix and then thinking about different points for the true parameter. Maybe that's something that may not be immediately clear to people, but that's their focus.
Yeah, that's thanks for clarifying that. Yeah, in fact, so this is kind of a either a theoretical question or it's just a exposition ease question, which is so why exactly so if we start with the zero set of K and where and the exposition go via studying singular model, which is where K is degenerate, has this degenerate Hessian. I think people who are not familiar with singular learning theory might object that that's a set of measures zero, and why do we care, right? But these plots are meant to illustrate that even if your true parameter does not lie on that set where the Fisher information matrix is degenerate, you are still massively impacted by the fact that there is a non-trivial set where the Fisher information matrix is degenerate, right? So let's look, for example, the behavior out here is that even though the true parameter is not on the set, so I think we need a name for that set. I'm going to call it the singular set or something for now. It's not on AB equal to 0, but at finite n, even at 5,000 n, 5,000 training sample, so we know that if n is big enough, it's going to look like it is far away. Yep.
Sorry to interrupt you. I think we should call it something like Fisher degeneracy locus or something like that. If we just refer to it as the singular set, since singular set or critical set usually refers to a function, it'll be very tempting to think about it as being associated to K. So I think it should be something like Fisher degeneracy locus, let's say.
Fisher degeneracy locus. Okay, Fisher degeneracy locus. Right, or degeneracy locus if I'm in a hurry. Right, got it. Okay, so even if so this may or may not be what Watanabe meant by so what is that called again? A discovery process, which is as n becomes really large, if your true parameter is not on the degeneracy set, it's going to look like locally it's going to look like a regular model. But if n is small, then the fluctuation of the log loss function or the posterior is going to be big enough that it's going to have a very non-trivial mass, non-trivial density on the degeneracy set. In which case, these parts, so the point AB equal to 0, 0, the origin is a singular point of the Fisher degeneracy locus, and that's where the RLCT is that's where things are most singular, and the RLCT is the largest. Wait,
I think that was a bit confusing the way you said it. That point is on the Fisher degeneracy locus, and if the true parameter were there, then the RLCT would be lowest. Is that what you mean? And when the true parameter is over where it is, then I guess that's actually a regular model, right? So W0 is 2 points, maybe.
Yeah,
maybe
W0. I think I'm trying to connect this story. So this is this might be not a fully fleshed out story yet, but this is very much like the case where we're talking about in our phase transition story, which is we still have non-zero L the likelihood of is non-zero.
Oh, I see. You're saying that the Fisher degeneracy locus, that is the union of the axes, is not, so that's some other level set, but that level set has a lower RLCT at that point, and therefore
exactly
that phase can still interfere with the sort of true parameter, which, okay, I see what you're saying.
Yeah, it can still interfere with the level set of the true parameter, and if and clearly in this plot, clearly some sampling, there is a non-trivial amount of probability that we sample a particular training set that favors the singularity more than it favors the actual true parameter.
That's interesting. I hadn't thought to make this point using what we've been discussing lately. Yeah, that's interesting. Do you mind if I put something on my personal board here and just illustrate this in case it's not clear to everybody? So,
sure. That's the spot.
So let's make this point actually the origin. So this is W. So that's the origin. And then that's actually the true parameter. You want to label that on your diagram? That's was that W0?
Well, the true parameter is A naught, B naught, but yes, W0 is fine.
Yeah, okay. So I'll just put that on the plot. So there's W0 and there's 0. So that's W0. And Edmund's pointing out that even though L favors the true parameter, of course, so we have something that looks like this. Maybe. Correct me if you think this is wrong, but
that's correct. Yeah.
So Edmund's saying that ln should and does favor the true parameter, but ln isn't in charge completely of where the posterior concentrates, because there's also the question of the RLCT. So maybe I'll just not completely.
I think more precisely. I think a bit more precisely, I should say that it's L that favors W0 more than it does favors 0, but ln, which is the stochastic version, depends on what kind of what data set is chosen, right? So there are times where we happen to choose a data set that for which ln actually favors 0, and that's influencing that's influencing the the free energy, right? Because the free energy is taking average over the training sample, hence 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 the fluctuation is kind of important.
Yeah, but favoring the origin is kind of begging the question a little bit, right? So why does it favor the origin? Well, okay, there's I suppose there's two contributing factors, isn't there? One is simply that it's stochastic, so who knows, maybe it ends up favoring it. And the other is that it may be that even for quite large n, there's a regime where it favors sampling near 0 simply because the RLCT here is much less. Right?
Yep.
I don't have this clear in my head exactly, but suppose the RLCT of that level set is much flatter, as I've drawn it, then you could imagine that even for mid-range n, I don't know what that means, you could still have samples that prefer to concentrate around the zero rather than around the true parameter.
Yep.
Sort of consistently. I mean, I don't know how to disentangle that from, like, what other reason could there be for the samples to, I mean, they could just happen to be concentrated around zero, whatever that means. But that's one reason why they might do it.
Yeah, and I guess the free energy formula is saying what happened on. Sorry, the free energy formula itself is it's not taking average over all possible data set, right. But then there is a fluctuation term, and I think the story here that it still remain a story without proof is that the fluctuation term is accounting for the fact that sometimes we happen to sample things that favors the singular case, and that fluctuation, the size of that fluctuation, whether or not that takes over, depends on the balance between between the n-ln term and the lambda log n term.
Right.
Yeah.
Yeah, cool. Thanks. This was a very illustrative discussion, I think.
Yeah. Okay.
Cool.
Cool. Right. So, okay, let's go back to the board. Which go back to the third board. And so I'm hoping that people are satisfactorily motivated to study the behavior of Kn. To study behavior, and now we are going to get into main formula 1, which gives us a handle to the behavior of Kn, which is a normalized version of the log loss. So to study the behavior of that, we introduce a stochastic process that is centered and normalized, or we call it psi. So it is given by this formula. So it's Kn centered around its mean. So don't the expression is not completed yet, but this part, remember, this part converges to the normal 0 sigma of omega. So that's by central limit theorem. But then we normalize it by this term, and this the only reason I think this is not the only reason. The main reason this is introduced, I think, is to make the variance at W not a constant. So that's I need to go ahead and actually do the calculation and prove this. But so recall that the numerator term converges to a normal distribution with some variance that depends on W. But if so, in the proof of main formula 1, we will see that introducing this term will just divide that variance out and make it a constant, at least on W0, on a set of true parameters. Actually, it's in the pullback of W0 by the resolution map. Right, but also this terms also makes it makes this process undefined, where so this is undefined at k of W equal to 0, which is the set of true parameters. Okay, so there is a exposition question here, which is, what if we just don't work with the normalized version? What if we just work with ln, and then we don't have this divide by 0 problem? but I suspect the problem will arise in the variance as well. So this makes it clear that we are traversing a well-lit path, and all the different branches has been like unproductive branches have been culled. I'm not sure.
Yeah, I don't know the answer to that.
Yeah. So Anyway, let's traverse this path for now, and let's look at what this gives us. If we rewrite this and see how this massage can into convenient form, we get this expression. Right. So these are all these terms are all deterministic terms, and this term handles all the stochasticity. And if we recall the proof, the attempt at proof of main formula 2 from last week, this form is to be used in the main formula 2. In main formula 2. And just to remind people what that looks like. So the main formula 2 is that we want an asymptotic expression for this integral. Okay, dx dy. Sorry for the poor board presentation, but and if you compare, spoiler alert, the resolution of singularity is going to give us this term here, and the square root of that is going to give us this term. So, and then that resolve into the C of xy, and then if we can prove that, if you can prove the main formula 1, and we can substitute it back into the current asymptotic we have for main formula 2, and get the asymptotics for the free energy, and get a free energy formula. Right. So this is one motivation for proving main formula 1. Right. So we have that psi n converges to psi. So this this central limit theorem convergence, pointwise convergence to a normal distribution, can be strengthened into a convergence of psi to a Gaussian process. But only only away from the set of true parameters. However, because statistical learning theory is mainly about discovering the truth, we do need to know about the behavior of this process, of this fluctuation near the set of true parameters. Okay. Okay, let's go to the next board to illustrate the main idea of doing that. So the main idea, to put it a bit colloquially, is to use resolution of singularity, the theorem from algebraic geometry, that is our favorite, to colloquially factor out zeros of QW. This is in the same way we factor out zeros from holomorphic function. For example, we know that sin z on z, the limit of sin z on z as z goes to 0 is 1, and that's saying that sin z is equal to z times g of z, where g of z is holomorphic and non-zero. Non-zero locally near the origin, and still holomorphic. We are going to do a similar operation to this, except we have multiple variables, and we have a very complicated non-isolated set of zeros. Right. So let's write down a statement for main formula 1 and see how this is related to the idea of factoring out zeros. So theorem, whoops.
That'll make Kenneth happy. He often does that.
Yeah.
It's not just me.
Yep. Right. Main formula. So given a model P of X W with W in a space of parameter, which is subset of R to D, and sorry, I think in the proof it is needed that this is contained in an open set, which is contained in R to D. Well, it itself is compact and has a open neighborhood. And truth Q of X, which is realizable, X given W naught for some W naught in the set of true parameters in the zero set of K of W, satisfying some, I'm going to be a cop-out and say mild condition. So this is a massive asterisk here. Then there exists epsilon, positive real number, such that the epsilon neighborhood of the set of true parameters, and I think this is defined inside the open set. Then this set, this epsilon neighborhood, can be resolved by a resolution map. So that in every local chart, so those are local chart. K composed of G is normal crossing for some K, for some multi-index K. And so this is where the zero get factored out. And using the same resolution chart, f of x w, sorry, I haven't defined f of x w, haven't I? So f of x w is just the log likelihood ratio. It's that term. And notice that f of x w, q of x, the mean over the truth is the k function that we want. So using the same resolution map, this term becomes, we can factor out the zeros and that is a ls cubed valued real analytic function. Concretely, that means that we have a power series expansion with coefficient, this x u to the alpha. So power series expansion in U and with coefficient in LSQ. LSQ is the space of norm S integrable function. Okay. Right. And then finally, using this property, we can define, we can get an expression for Kn in the resolved space, resolved parameter space, as u to the 2k, then u to the k, Cn of u, where this stochastic part is defined everywhere on this blob space, and is defined using just the factored part of f. Is equal to that expression. Okay, so let's go back to the first board, and we'll just finish up with an outline of the proof, with the steps that's needed for the proof of main formula 1. So outline of proof is to first just get the resolution of singularity, singularity for k, and this is at the epsilon neighborhood of W naught, which we call W epsilon just now. This is guaranteed by Hironaka resolution of singularity and its extent, and the diversion for analytic function, right? And this gives us the map, the resolution map, such that kg of u in every local chart is normal crossing, right? Step 2, and that's kind of the core step, well, beyond the resolution, and it's theorem 6.1 in the gray book, is that we show that this expression, let's define AXU to be equal to the expression, and show that this expression is analytic, right? And a crucial step in here is by realizing that this expression is equal to kg of u, which is equal to u to the 2k. Right. And once we have that, we will just define the random process we have before. Sorry, these are some of the eyes. And so this can be taken as a definition once we have A, and observe that if I multiply this, multiply it by u to the k root n, so the root n disappears, and I get u to the 2k u to the k. Well, that's just f of xi of u, and that's kg of u. So this is equal to n lots of kg of u because of the summation minus n lots of the kn function. Right, because that's the sum of kn is the average of the xiu function. All right, and then we need to show that this random process is defined everywhere and everywhere on the blow-up manifold. And the crucial step in that is to show that AX, I'm going to write U naught. The second moment is 2, is a constant, right? And U naught is in the pullback of the set of U true parameter. Yeah. Okay. So that's the outline of the proof that we will go through next time. And there's a few to do, which is the main thing is to prove main theorem 2 next time, and also to illustrate where the mild conditions of this proof comes in. It's called fundamental condition 1 in the gray book. It involves extending this f function to the complex plane. I am still not very clear why that is strictly necessary. And yeah, and then finally, we do need to invoke some results from empirical process theory or just stochastic process theory to show that these things do in fact converge to a Gaussian process. And that's that completely characterize the behavior, the deterministic behavior, as well as the stochastic behavior of Kn in a neighborhood around the true parameter. And right, that's it for today. Any question? No worries.
Yeah, I guess I also don't know the best way to communicate what's going on with C here. And what's your intuition about dividing by the square root of k? I mean, I guess I understand where it comes from in, say, the central limit theorem, for example.
Yep. Well, I actually cannot. So in the central limit theorem, we can get an expression for the variance, right, in terms of f and the parameter. But I don't think that is square root of I don't think the standard deviation is exactly square root of k. Maybe that is true in the set of true parameters, and that's the only reason he introduced it that way, because we really just care about what happened on this. We just want C to be defined on that set. Everywhere else, we are fine. So that might be the reason. And also the place where it shows up is basically in this integral here, right? That's where we divide it out and exactly make the variance constant on the pullback of the set of true parameters.
Can you say that again? In what sense have we made the variance constant? Oh, because that. Yeah. Right,
yeah. We don't want it to have dependence on U or W anymore. One, it makes it very clear that this stochastic process is defined on U naught and hence on W naught. Yeah, I think it's kind of a standardization term, but only for W naught and U naught. That's my intuition at the moment. That's my guess at the moment. That's the only reason.
Yeah, I think I don't really even know how to. So if I set myself the exercise of explaining to a deep learning person what Xi means in terms of trajectories or something, I think I wouldn't be able to do a good job of it. I can technically understand the role it plays, but like kn minus k is something you could explain to somebody, right? In terms of, it's
yeah, that's kind of the first exposition question I asked. Like, why? Like, even that is a bit suspect, which is like, why? I think a deep learning person might ask, why don't just work with L, right? Work with the log loss. That is the measurable thing, and that is the thing that we can get from experiments, and they only, like in their experiments and most of the quantity they compute, they only use L. And as I say, like introducing k gives us the problem of dividing by 0 when we introduce the root k of w, and why did we do that?
Well, let's see. Yeah, fair enough. I mean, I guess if you're working near a true parameter, k is the thing that sort of just has the second order part from the Taylor series expansion, right? So I think it makes sense to talk about k in local coordinates rather than L.
Right.
It's just sort of getting rid of the 0th part of the Taylor series expansion, right? I mean, that's a normal thing you do when you're studying functions, right? When you talk about singularities of a function, usually you just shift the function so that it's 0 at the origin. That's all I thought about the focus on k.
Yep, definitely. I think even deep learning people will sort of engineering people would accept that focus on k. The thing that I'm not sure is that it's actually the definition of of psi, because like we introduce the denominator there. So why not just take ln minus L, and then normalize that somehow, because L is never 0. Is it never 0? Actually, we don't know that. Actually, L can be 0.
Yeah.
In fact, L can be can L be negative? Wait, no, L can be negative. Yeah, L can be negative, right? Yeah. Even Ln can be negative, right? Because those are all positive terms. Because those are all probabilities. Wait, that does mean that Ln is never 0 and L is never 0. It's a sum of positive terms.
It doesn't strike me as the main thing to worry about. I guess I'm thinking about in the regular case, when you look at what psi is in the regular case, somehow it makes a lot of sense to divide through by u or square root k, because what you're looking at is a kind of dot product, and then you just getting the actual interesting part by dividing through by u.
Mhm.
I couldn't figure out so in the regular case, it's very clear that's sensible and what that means. In the singular case, I think I still don't really have a good intuition for, well, anyway.
I should do an exercise with a regular. Is there a singular case for that? Yeah, right. There can be a singular case for a one-dimensional model, right? So
Yeah, that would be useful.
yeah, and see what happens. Like we don't have this multivariable things to be concerned about, and just contrast the regular and singular case in that case and see. Yeah, and see where the square root comes in.
Yeah, even just with a cubic or something. Rather than
What do you mean?
quadratic.
The cubic?
Well, have an exponential model where you're just looking at the graph of x goes to x cubed rather than x goes to x squared, which would be
right.
Which would be regular.
Yep.
Well, thanks a lot, Edmund. That was really useful.
No worries. Thanks for uploading the pictures. Yeah.
You didn't show us that other picture. Tooth.
It's meant to be where I show. It's meant to be where I show the idea of factoring out the zeros. But I meant to like write things on it. But yeah, that's okay. Yeah. Wait, where's the blob? Oh, blob is on the other side. I meant to show that like let's walk to the other side. I meant to show that this part, like, so that's the circle part is meant to be kind of a chart, a local chart, sort of the preferred local chart that we would be using after blowing up, and it would look like normal crossing like that. And in fact, it's further divided out into these charts. Yeah, so in n dimension, it's divided out into 2 to the n. Each neighborhood of a singularity is divided out into 2 to the n of those. Yeah, and that's ultimately what will happen in the sort of a center part of the free energy formula, which is sum over the alpha star charts, and these are where things are most singular. Yeah. Yeah, that's why I meant to show that. Yep. Cool.
Yeah, I think this picture is a really good one for illustrating this choice of adapted coordinates, or whatever it is Watanabe calls them.
Wait, it's not. What is it? Adapted coordinate?
Oh, that's just a standard term that gets used for choosing coordinates that are useful. I don't think it's what Watanabe calls them much.
I see. Right.
Although, I guess at least for me, the way coordinates work in the story is a little unusual. I mean, usually you think about choosing coordinates on open patches, and in fact, you've kind of drawn it like that here, right? But really, it's coordinates on this. Well, I guess you're right that he chooses on either side and then splits it up, but somehow it's more like that quadrant rather than having a little bit on either side.
What do you mean?
All the u's that appear in the formulas are never negative, right? They're always measured from one of these lines. So there's that would be u1.
Yep.
And it's never negative, and that would be u2, and it's never negative. And to talk about over here, you actually switch to a different coordinate chart. I use this word chart, but it's not a chart in the usual sense of introductory differential geometry, where you talk about open sets and local coordinates. It's So
It's half open, isn't it? It's always like 0
that's
b
right.
to the
That's right.
to the d or something. Yeah.
That's right. So those are the sort of neighborhoods that Watanabe is using.
Yep.
Yeah, I guess he treats this to various degrees of care, right? So like in the WBIC paper, he's super careful to talk about which half he's using, and he has some parameter. I think those are like epsilons. I don't remember. To talk about whether he's in that half or the kind of other one. In the Gray book, he just kind of drops this at some point and just doesn't worry about it. I don't know in the Green book whether this is. Does this choice of coordinates and the way it works ever get described in the Green book? Maybe not.
I forgot. Like it, I won't be surprised if it is not, because the proof for the first couple of main formula is basically saying that it's trivial. No, I don't remember, but I'll look through it again.
All right. I'm going to take a break for a few minutes. We'll come back at 11:30 AEDT for the working session, or you got to run, Edmund?
I might need to run. Yeah, I need to pack.
yeah, do that.
Yeah.
Are you be there, Ken?
Yep, I'm here. Come back in 20 minutes.
Yep.
Okay.
See you then.
Cool. I'll see you guys next week.
Yeah.
Bye.
Thanks again, Edmund. Catch you later.
No
Have a
worries.
safe
Bye. Thank you.